Hello everyone, this is Mr. Jackson, and today we're going to be going into Module 3, which is going to be all about the circulatory system, primarily the heart. So while our lecture today is going to be primarily looking at the physiology or the function of the heart, we do have to build that on a strong foundation of the anatomy of the heart. And so we will have covered the anatomy of the heart in person in class through a few of our activities, but I did want to provide this slide so that we could pause if we needed to, do a quick review of the basic and most important structures of the heart, namely our left and right atria, which are those receiving chambers, and the left and right ventricles, which are those discharging or pumping chambers. So we need to understand that we have, in addition to that, those heart structures, we got to understand that we have a systemic and a pulmonary circuit where blood is either being pumped to or from the lungs, from the pulmonary circuit, and to and from all of the other body tissues in the systemic circuit. Okay, and so you will know that you have a firm enough understanding of heart anatomy if you are able to trace the pathway that a red blood cell would take from the time that it comes from the lung as an oxygenated blood cell to the time that it is returned to the lung as a deoxygenated blood cell. So if you'd like to hit pause on this video and do a quick review of that anatomy, please feel free to do so. We're going to be building on that now. So of special importance in our physiological discussion is going to be those AV valves as well as the semilunar valves. So those structures in your heart that keep things flowing in one direction. Wanted to make sure that we identify how those are behaving throughout a single cardiac cycle. That's like namely one heartbeat. And we're going to be diving into the steps that are involved in that as we move forward. So whenever you think of your AV valves, right, those atrioventricular valves between the atria and the ventricles, remember on the left side here, we've got our bicuspid, so two cusps, and on our right side between our right and left ventricles, we have the tricuspid valve, okay? This does a really good job visually of showing you what's happening. So And you can feel free to hit pause if you'd like to take more time with this. We'll go through it really quickly. But we basically have blood initially returning to our receiving chambers, those atria. And all that pressure of the blood filling those chambers is going to create pressure that basically keeps our AV valves closed. All that, as that pressure builds up, it's going to actually, the valves are initially closed, and it's going to actually open those valves whenever the pressure builds to a certain point. Now, once those are open, the ventricles are going to start receiving blood. Okay, so they're going to start filling. And those AV valves are just going to basically be hanging loosely while blood is filling those ventricles. At a certain point in this cycle, the atria are going to contract, therefore forcing additional blood down into the ventricles. And it's important to understand that while these valves are open, that is basically meaning that the atrial pressure, the pressure inside the atria, is just greater than the pressure inside the ventricles. That's why those valves are able to open and remain open while they do. Now, at a certain point, those ventricles are going to fill to a point where they are, filled with enough blood. And a second part of this process is those ventricles are going to contract. And so when that happens, this is going to force blood up and against those AV valve cusps. And this is going to cause those valves to close. Now, that pressure is very, very, very large whenever those ventricles contract. And so it's important to also point out some key players here, the chordae tendineae, which tighten and prevent those valves from turning inside out and allowing blood flow or backflow back into the atria. Okay, so during ventricles contracting, those AV valves are closed, and at this point, the reason why that's a possibility is because the ventricular pressure has become greater than the atrial pressure. The Semilunar valves are the ones that are essentially following the ventricles, okay? So the ones that go from your right ventricle up through your aorta, or your right ventricle up through your pulmonary arteries, or your left ventricle up through your aorta and to the rest of your body tissues. So what's happening with these during the cardiac cycle? So as your ventricles contract and that intraventricular pressure is going up, blood is going to be pushed against those semilunar valves, and all that pressure is going to force those valves open, again, in an upward single direction. So this is what that would look like whenever those valves were pushed open. And as the ventricles are then going to relax after that contraction, the intraventricular pressure is going to fall. Blood flows back down from the arteries because we're no longer actively pushing blood through them. And so that blood is going to come back, and as the blood comes back, it's going to hit against those cusps and force those semilunar valves closed again. Okay? So that's really, really important to understand how those valves are behaving, because they play such a key role in preventing any sort of backflow. They keep things moving in a single direction. Now, we also have this intrinsic conduction system, right? This sort of nervous side of things that basically keeps the heart itself contracting, right? So the cardiac muscle itself is able to spontaneously and independently contract regardless of having outside nerve impulses. And that's really, really important because it basically shows the priority of keeping this organ going regardless of what's happening outside, or if there's any sort of interruption in nervous input, we can keep things going so as to preserve life. Now, these contractions are going to occur in a regular and continuous way based on what chambers they exist in, right? So you have the atrial and the ventricular cardiac cells. These happen to beat naturally at different rhythms, right? So your atrial cells up top in these receiving chambers, those cells are regulated to beat around 60 times per minute. So that's about once every second. But your ventricular cells would naturally, if left alone to their own devices, your ventricular cells would beat only about 20 to 40 times per minute. So a lot slower compared to the atrial cells. So because these rhythms would naturally be off, we have to have this sort of internal unifying control system to keep everything beating at a set rhythm, right? In a coordinated way. And so there are two ways that we can regulate this heart activity that we're going to discuss today. And that is either through your autonomic nervous system. So that's, that nervous system input, right? Again, it's from that autonomic branch of the nervous system. So we don't have to consciously, think about it. It's going to keep things going, based on the conditions of our other organ systems surrounding the circulatory. But then you also have what we're going to focus on here, which is that intrinsic conduction system. And this is ultimately going to set a heart rhythm. It's composed of special nervous tissues that can work independently of your ANS. And this is what's going to basically make sure that your heart muscle depolarizes in a single direction, starting at your atria and then down into your ventricles. And this is also going to enforce a heart rhythm of around 75 beats per minute. And this follows a very simple sequence that we can review real quick. So I'll go through this 6-step process. As I go through, I'll just basically be over here highlighting the main structures and showing the direction of those impulses. So basically, we're always going to start with what we call the SA, the sinoatrial node. That's your pacemaker. That is going to supersede all of the other cells to maintain a constant rhythm, because the rhythm of the SA node is inherently quicker than the other atrial cells, or the ventricular cells especially. It's going to basically maintain a set sort of pace for the entire heart tissue, and it's going to also be our starting point up here in the atria, and it's then going to spread down from atria to ventricles so that we have that wave-like depolarization, we have that wave-like contraction all coordinated. So it goes from the SA node, which is your pacemaker, spreading through the atria. Eventually it's going to arrive at this AV node. Okay. The AV node is then going to transmit that signal further down through the AV bundle, also called the AV or the bundle of His. At this point, as that wave of depolarization reaches the AV node and beyond, these atria are contracting. At the AV node, we're going to delay the impulse just briefly. That allows for some ventricular filling to occur when those atria contract. Impulse travels through the AV bundle, down your bundle branches, and then throughout your Purkinje fibers. And once this wave reaches those Purkinje fibers, this is going to cause a uniform contraction of your ventricles, and therefore blood is then ejected from the heart. And so that is the stepwise process of this internal conduction system. Two really important key terms when it comes to physiology of the heart. We have both tachy and bradycardia. Tachycardia is a term that basically refers to a rapid or elevated heart rate. This is typically over 100 beats per minute. Bradycardia is referring to the opposite. This would be slow or lowered heart rate, and this is going to be referring to a heart rate that's lower than what we would expect at resting, which is typically around 60 beats per minute. And we're actually going to, for time's sake, we're going to break this into two parts. So that's where we're going to leave part one. Whenever we pick up in part two, we're going to be going specifically into the cardiac cycle and breaking down the steps of that. And so we'll see you at the next one.